next month I'm overseas lecturing, and rather than trying to deal with tips, we thought it was smarter to cancel for next month, and the month afterwards we didn't think we'd get too many takers for a Christmas Day meeting. So don't know why, just one of those things.
I would be there.
And I would be anything not to be with the family on Christmas Day. I don't think it's Christmas Day actual though, unfortunately, otherwise we might have kept it, Peter. Looking at trees, insects.
We got a few examples, photos. I don't know if you've had a chance to look at them.
Yeah, I have certainly had a chance. So if I go to share, hopefully this will let me do it again, Peter.
Yep.
Looks like it's going to. Okay. And hopefully I've got the desktop. So if I get that right, and I say Windows key D, you can see a lizard. Yep. So we are in the right spot then. So we want to have a look at some emails. And they were largely from Derek, and I don't think Derek's on the line and with us yet.
Yeah, we had a couple of people share.
Yeah, there was quite a few there from Derek in one go, but we'll go back to, I'm pretty sure this is it. So here is a fine example of canopy reduction pruning in Mansfield, Victoria. Is this something that arborists should get involved in by complaining to councils when not involved in this butchery? It's a hard one. Hopefully you can all see the image. I'll zoom in a little bit and then I'll make it a little bit clearer if I can. It's probably not the best example of reduction pruning that I've ever seen by a long way. But the nice thing is at least one of the cuts was correct. And I think you've got to give points where points are due. This cut here is in compliance with the standard. I don't know whether you can see where my mouse is, but that top reduction cut is within limits. Look, it's hard to say how you deal with this. And it'd be interesting to hear from those that are involved in local government. But you've got to be very careful when you're being negative or critical of other people. Now, does that mean you shouldn't be? I don't know. My personal view is at some stages, arborists, we need to make a stance. And I would probably have some concerns about this, and I'd probably express those concerns to the local council and maybe even the media to say, look, this is not good work. But is this horrible? Is this beyond the pale? Is this beyond acceptable? I don't know. What do you think? And I'll give you some comparisons to have a look. So
I wouldn't be surprised if the tree doesn't survive.
Yeah, I would be quite surprised if it didn't survive. And it may have some problems, but I thought I'd just share with you a couple of counter trees just to let you get an idea. And if we look at, if I can, Taroom in northern Queensland or middle Queensland, Taroom, and go to Leichhardt's tree. It's one of our most important historic trees in Queensland. And you can see that it was locked. Go on, be a pain. Don't open up quickly enough. Yeah, if we go back and have a look at it, and there are historic images of it. Let me find one that's a little bit better. Okay, let's see that will open now. Yes, you can see here the tree was lopped to quite extensively. And if you go and look at the tree today, the tree does look substantially different. And it was one of those quick trips up north, and we'd finished dealing with the council in the northern New South Wales area. And I said to my wife, what do you want to do? And she said, I don't know, it's Friday afternoon. I said, let's drive on to Taroom and have a look. So we did. And this is that same tree. Now, is it perfect? The answer is no. but it does have, I think, benefits still. And I'd suggest it probably was locked one more time after that, that situation.
I know of some trees in the streets of Lismore that were heavily locked in the past that have regrown and are basically sound, healthy trees now. Yeah,
look, I don't think that it's the end of the world. And one of the reasons I don't think it's the end of the world is in the Australian standard, it talks about this thing called restorative pruning or restoration pruning, which is when, a tree is damaged by, for example, winds or storm. And again, that goes back to that discussion we had last block, I think, Peter, about breaking roots or not breaking roots. It was amazing in the 1991 microbursts of Sydney, 50,000 trees were blown over. That's quite a few. But there are also a whole pile, their tops blown out and they were damaged. And probably a third of those were pruned or repaired in some ways. Probably a third were removed, maybe more. And then there was a portion where, for whatever reason, the householder never did anything. And can you believe it? Some of those trees are still around. They're grown back and they've dealt with it and they've, responded appropriately. So, no, it's not perfect, but it's not the end of the world. So yes, going back to answer that question that was asked, should we be getting involved? I think there are probably times when we should be very careful. I take heed to those words of Dale Carnegie. I'm not the best at following it. So, and that's never condemn, criticize or complain. It's easy, and particularly don't make it personal. So it's not that the arborist is the worst arborist you've ever seen. It's just that this work perhaps could have been done a little bit better than what it's been done. Perhaps the pruning was heavier than it should have been. Be careful on how you express it. Having said that, I'm never the best at figuring these things out. And I saw a document on Saturday that made my blood boil. It was a publication written by an arborist, and it just didn't look like something the arborist could write. And I did a plagiarism check on it. 35% of it came back automatically under a plagiarism failure. Probably 75% of the document was copied from the internet, just pasted into, and his name put on it. And so that made me do a little bit more searching, and I looked at his qualifications and I thought, well, that's a really interesting qualification. He's got a graduate certificate in urban parks management or something like that from UTS. And I thought, well, that's interesting. I should find out what was involved in that course. Now the course doesn't exist. And I thought, well, hang on, this is really getting to the stage that, where do we put our foot down? Do we put our foot down and say, hey, this is just damaging our profession? Now, there are others that would say the same for me. There are others that would say, well, hang on a Mark. I've been to your old webpage and I've seen you've got Sir Mark there. And the answer is, yeah, I do. But I don't relate it back to my activities. It wasn't that long ago, Sir William Hume Bart the 14th, English baron, was giving evidence in court, and he's an arborist. And the judge turned around and said, or the commissioner turned around and said, well, I'm not going to call you sir. And I thought, isn't that fascinating? Because if that was in England and he even said that, he'd have been chided by the judiciary over his insolence. So there are going to be things. Now, William's baronetcy is not associated to arboriculture. So, perhaps there's an argument there, but he still is entitled to the title as much as a judge or a commissioner is entitled to the use of their title. So I guess these things are subjective.
One thing that comes to mind looking at that tree, Mark, is that it's possible one scenario is that the residents were frightened of it. Whether or not that's justified is a different matter, but they were frightened of it. So they wanted it reduced. And if you couldn't reduce it to that extent, then they would have been it's likely that they would have been trying to remove it. So even though this isn't great, at least it's still there.
Yeah.
Hi, Peter. Hi, Peter. It's David Caronia here. I was the one who sent the photo in.
Yeah.
David.
bit of background. This guy has systematically gotten rid of all the trees around his house, and this is the last one he got pushed and got one removed next door, and he's done one in his backyard, and yeah, just systematically removing them. And yeah, I think you're right. He is scared of them. You know, I spoke to him at one stage, and he was, these trees haven't got a place in, around houses, etc. So yeah, I guess that's where he's coming from. When you see failures in red gums around the place, yeah, he probably is scared.
Yeah, look, and again, thanks for that, David. It's the Compartmentalisation from that comment then.
Yes, that's correct.
Compartmentalisation. Yeah, look, again, this goes back to a whole pile of things that come together. So, for example, we allow building under these trees. We don't require our buildings necessarily to be spec'd appropriately for building underneath. So this has got a metal roof, which is really good. I think that's great. A metal roof with 450 mil centers on the trusses, very strong, very hard to break in comparison. So, we're halfway there. But I think that the level of risk is really still quite small. I was in New Zealand earlier this month talking about risk over there, and I said, how many of you have been asked the question, when did you last get your trees inspected before you paid your insurance premium? And one person out of the 22 that were there said, yes, I've been asked about having trees around my property, whether I had them or not. They asked no questions as to whether an arborist had inspected them. But I'll go back to it again. The risk from trees is so small that I often think these things aren't directly risk related. I think if you said to him, look, we can put a magical set of sky hooks in, the tree will never fall down. The next thing would have been, yeah, but they dropped bloody leaves in the gutter and there's a mess, and you can't see what I've got to clean up all the time, and it's dribbling bloody sap on my car, and all those sort of things will start to come out.
Yeah.
So it is a hard balancing act. And to some extent, we as a profession have been guilty for promulgating those sort of concepts. That many an arborist have said, in fact, I think I've shared before, my very first day in a diploma classroom, the lead teacher for the course turned around and said, there's no way I'd have a big gum over my roof. And I thought, boy, well, I've got a big gum over my roof and I just want more. Maybe you shouldn't be teaching it. And I shared a few minutes ago about a young gentleman who decided to copy and then lie about his qualifications. And I made the comment because I ended up doing what you end up doing and stalking the person. So I said, I've been told that people who don't have trees shouldn't be arborists. And I said, I'll make a wager you don't have anything more than a metre-high Buxus hedge on your property, which is exactly what it's got. I mean, how can you be an arborist and not want to have trees around you? That seems to me something that's grossly incongruous. Now, I know if you're renting, I know if it's but even if you're renting, I'd want to sabotage, and I certainly did when I was renting in the earlier days. I don't want to be in a treeless environment. So yeah, thanks for sharing that, David. And yes, I think if you want to get involved, be gentle, or be prepared to have roller shutters on your front of your property, set your house back a fair distance, put ballistic glass in the front. I think you've got to be aware that some people will get quite hostile, and I've certainly had a few threats about expressing my views on things more than once. So just be careful of that. Okay. These ones I'm just going to have to zoom in a bit more because they're a little bit small, and hopefully images. This is a tree that Derek Williams, I don't know whether Derek's online, but he suggests this might have been hit by lightning strike. If there's something that gives the hint that it might have been, what might it be here? Anyone?
Bark peeling off.
The bark coming away. Yeah, look.
And the curve.
The spiraling, yeah, there's some spiraling there, but it may not be. That may just be a load failure of some description. So it's hard to to know for certain whether it's lightning strike. It might have been a little easier straight after the event, but yeah, it's a little bit difficult to say whether it is or isn't.
To help you out, Mark, people were watching it. When it this one was a witness.
Okay, so sorry to get hit. Yeah, look, and again, I still even treat that with a degree of skepticism on occasions, because I've had people say to me, oh, you know, we saw the lightning, we saw the thunder. If they say to me, oh, look, we saw the lightning and our fuses went out, we blew out like globes. At that stage, I'm absolutely convinced, but the number of times I've seen a co-dominant stem with included bark fail, and the people tell me that they know it got hit by lightning, is quite high. Correlation and causation becomes the issue again. People see it during a storm, there's lightning in the area, and the tree splits apart. Their assumption is the two are related, even though they may not be. So being able to see it's good. The best, of course, vision nowadays is when it's recorded by video, and that works really well. This, on the other hand, is another one of Derek's, and there is no question that this is lightning strike. Oops, let me just try and get it to a scale that's good for image quality. But so yes, there's a nice zigzagging in the bark. The bark has been blown out, and we used to think that the bark was blown off because the vascular tissue underneath boiled. That was the old theory. We know now that's wrong. It's actually the pressure wave. And it's that pressure wave that's created by the air being pushed out as the bolt's going down that causes the damage. Pushed out and coming back together, that bang that's associated with it. It's not the heating up or the cooking. So this is a percussive damage. This is, you know, something being hit hard. And Peter, you may remember a guy, Bill, in one of our classes. Bill,
yeah, I do remember Bill. I can't remember his last name.
But we do a little experiment where we stain up plant material and then remove the bark. And Bill said, you're doing it all wrong. You just need to hit it hard and the bark will come off. And Bill was absolutely spot on, right? And so that's all that's happened here is the air has hit it hard. And if you start to get your head around the pressure wave, when you're watching these movies and you see them let off, you know, a big bomb, and, you know, one half has the door blown out and the person's made a mess of, and they're standing there on the side where the explosion was unaffected, you can sit there and laugh and say, well, that's completely unrealistic, because pressure works both ways. Another thing that was really good about this is some of the bark was taken off in whole whirls between the nodes. Again, just as a result of that pressure wave. So there's a bark cambium, and the bark cambium, or the outer bark, the phylem and phylloderm and phyllogen were pushed off. Or the phyllogen may still be there. It's hard to say, but certainly the phylem was blown off. So yes, that's definitely a lightning strike, and pretty obviously one. So great shot. This one, I think it's a great little shot. These guys are really quite damaging to trees on occasions. And it's not the best of image, and I apologize again. I don't know where the image quality got lost between Derek and Peter, or Peter and me, or whether it came out of Derek low res, but there's a yellow-tailed black cockatoos. And one of the things that's important to know about them, and you guys have them in Melbourne, I'm pretty sure, don't you?
Occasionally, yeah.
Yeah. We have them in Sydney occasionally. They don't, although there's in the eastern suburbs, there's actually a really good breeding colony. But these are insectivores. They're like insects. So they're actually doing a beneficial job here. They're taking out Phoracantha larvae. And in that state, they rip off the bark. And they're generally not like these sulfur-crested cockatoos that do habitual bark chewing. These guys are in that bark for one thing and one thing only, and that's food. The dilemma becomes when these guys find cossid wood moths. So along the east coast of Australia, Xylutes particularly, these guys will go in and they'll fell a tree to get them out. They'll take a tree with 150, 200 mil trunk and put it on the ground if that's what they've got to do to get the borer out. And they'll do that in 10 or 15 minutes. Quite amazing. But the other half of this shows the importance of trees ecologically. And, you know, we can oftentimes forget about how important some of these diseases that we have are elsewhere in the ecological system. Mm-hmm. So whilst we don't want a whole pile of borer damage, you know, we want the benefits on the other side, and that's the ecological diversity that comes with it. So there are unique wasps that go with borers. There are unique secondary issues that come with it. So it's not just a one-sided argument. Okay, so Peter says a white rot. Now, that's really unusual to know, but it almost certainly is a white rot. But what's really interesting is the fruiting body is white on the underside, and it doesn't look like a Ganoderma at first instance, but I think that's what it is, Derek. It looks like a Ganoderma, but again, taxonomically, and I know we discussed this last block round, these things are often very difficult to determine without DNA nowadays, but that would be my first guess on it, would be Ganoderma. There's a series there of wood decay inside, and they are all white rots. I don't know what sort of trees they are. Maybe Derek can enlighten us on that. But this is a white pocket rot that's led to failure, and that it can do. It's just not a common thing in a healthy tree. It's a problem when there's non-healthy trees.
Yeah, that was Angophora floribunda.
Yeah, okay. That damage has probably been sitting there for decades in that case, Derek.
That's right.
Now, bird damage. Bird damage is really interesting stuff. And the reason that bird damage is interesting is because it behaves in the same way as fungi does. It causes a stimulation. So there's some change in the things around. It's not as quick as it is, but when it's repeated, and it can be, and this almost looks like the ones in the park at St. Mary's, if I was guessing.
That's because it is.
Well, good. We look at this at QTRA training, and you can see the adaptive growth on around a lot of these cavities. So you can see here, for example, the thickening on this margin. And this is that process again of putting wood further out. So if you actually looked at this in cross-section, you'd find something like the Philinus paradox we looked at last time, where there's actually more wood further out, so it's stronger. This may not be stronger, but it may not be substantially weakened from the cockatoo damage either. So repeated cockatoo damage in particular is not necessarily an issue. The branch going over here, where it's this process of forming around and grafting around, is called inosculation when it happens naturally. There's a lot of extra wood there, but it's not perfect. It's over a seat. I'd shift the seat, Derek. Please leave me the trees. I need somewhere to lecture. But I'm gathering from what I heard that they might be going sometime soon. Is that right?
No, what we did was carry out a selective weight reduction proof.
I love
quiet
you.
up the damage, and the next process is to move the seat.
Yeah, look,
Which isn't easy because, you know, I'm all for population control, but we're keeping all the trees.
Well, yeah, we looked at the risk of this tree, and I think the risk of this tree came down to about 1 in 100,000 or 1 in 400,000. Can't remember. It was in that range. And you look at that and you say, well, hang on a second. Okay, let's compare that with car driving. Risk of mortality from car driving is 1 in 20,000. A risk of harm is about 1 in 10,000. And
so your 1 in 100,000 though is pretty high for a tree though.
And that's the dilemma. It's high for a tree, but it's low for a lot of other risks we accept in society. And so arborists would come out and say, this is if they're doing just a purely gut level feeling, oh, this is, and they do. I mean, I watch students go around and look at the trees and say, oh, that's high risk. And then you say, okay, let's look at it. What's the target? and the target here is weather modified 4, if I remember.
The
And then,
risk isn't high, it's just obvious.
yes, and it makes people feel uncomfortable. And so you end up with people, when they sit down and look at it, you say, well, okay, this is, 5 times lower than driving a car, and I can make driving a car safer. Who would like to know driving slower? I don't want to make you do that, because that'll work. If you drop your speed down to 40 or 30 kilometers an hour, you're a lot less likely to get killed. But just simply wearing a full face racing helmet will do the job for you. We know that because motorsport proves that. Okay, we've got lots of data to show you that a full face helmet significantly reduces your risk of death from a motor vehicle. But we won't do it. Why?
It's inconvenient.
Yeah, it's inconvenience, and we already accept that a risk of about 1 in 20,000 is fairly small. I mean, that's in a lifetime. I've got a 1 in 125 chance of dying in a motor vehicle accident, but I've got a 1 in 5 chance of dying from cancer or heart disease. Now, Michele, you'll understand this. I'm a little overweight. I think we'd agree on that. Can we just?
Yeah.
If I was really worried about my heart disease risk, wouldn't I go for a good brisk walk at least 4 or 5 times a week for maybe
Yeah.
half an hour?
You watch your diet.
What I try to eat fairly well. I just eat too much. But so yes, already as people, our responses to risk is quite interesting. And this week, the Society of Risk Assessors of Australia and New Zealand are meeting in Melbourne. I'm heading down to have a play with them. And, these are pertinent issues for them. We must be one of the most grossly overfunded risk industries in Australia based on mortality rates and based on incidents. It's just almost incredulous how much we spend versus how little is spent in other areas. And that's because we're talking about a risk of mortality from trees of about 1 in 5 million per annum. And I know that when I talk to people down there, I'm going to have them snicker and laugh at me because it is absurd. So yes, I think, Peter, you've made the right, sorry, not Peter, Derek, you've made precisely the right management decisions, and that is reduction. We valued, using that paper I worked on and finished the stuff, I think about a day or two before I last taught here. And we valued this Canopy, I'm pretty sure, at about $3,500 of health benefits a year. So it's providing about, at 100,000, providing about $50 a year worth of harm and about $3,500 worth of benefits, or a net of about $3,500 worth of benefits a year. You really couldn't remove it. It would be obscene.
Yes, this was the largest and the healthiest. It's in the middle of the park.
Yeah. And look, I mean, there's some other trees there. You've got cytoroxylin decline, obviously, as you've seen, but
yeah, that's been a problem after the wet weather. There was still a little bit of apprehension. So down the track, there's going to be 2 or 3 Cobra braces loosely installed in the canopy, so that if something fails, it'll hopefully hang up in the tree. That's made everybody happy because the original intent was to remove it. In that picture you've got there, there's a cavity that's 1 metre deep down inside that stem.
This one here, yep.
Yeah, that's the one we paid particular attention to for carrying out a weight reduction prune to reduce the leverage, because it's a fairly large cavity. Deep cavity. But we didn't, all of the original structure is still in place.
And what's really interesting is this wood here is that highly twisted grain that is really strong.
Yes.
And the other thing that we need to keep in mind here, this is spotted gum, Eucalyptus, Corymbia maculata.
Yeah, no, this was Citriodora, this one.
A Citriodora, is it? Sorry. Yeah. It's a Corymbia anyhow. It's a highly durable timber. So even while this is all open like this, there's not a huge amount of decay overall. Even the cavity is quite, whilst it's quite deep, is not spread very much. And that's because decay moves up and down in a tree far easier than it does outwards. And we saw that a block or two ago when we looked at how fungi moves through vascular tissue.
If that stem failed, Mark, say in a storm or something, I seriously, honestly would expect it to fail 2 or 3 meters or more up that stem and not at that cavity.
Oh, Peter, a number of times I've seen that sort of thing happen. And of course, if it fails a meter up here and there's decay in it, you know what everyone says then, don't you?
Oh, well, you should have known.
Oh, the decay was the cause of the failure. Yeah, look, it's interesting. And I would say that failed during a storm, which is, would we all agree that's when we'd expect that to fail? Most likely would be during a storm.
I would think so, because it's also fairly exposed.
Yeah, it is. Derek,
Potentially.
but in context, that the amount of people walking through that park when inclement conditions are in place would be how many? Almost nobody.
Yeah, you'd only have someone passing about every 20 minutes to half an hour.
So
There's no one.
And hang on a second.
In the taller block shooting up if there's a storm.
I'll just have a play now, and we'll just have a quick QTRA assessment of it.
Just while you're looking for that, Mark, would it be worth tying the tops of those stems together with a cable?
Yeah, that's what Derek suggested, putting a Cobra. Cobra is a dynamic system. So it's a polyethylene, if I remember, rope, but it's got flexibility, and you don't keep it taut. You just allow it to flex so that you still get strength developing, still get flexure wood, but it stops it from going too far and from failure occurring.
The only problem with doing that is that you do have to maintain it. And I know of those systems that have been put in place and left, and I just have not been able to get them properly maintained, and they end up 10 years down the track actually causing damage.
They can do. I did. Well, I didn't do it. I specified it for a historic tree in Liverpool in Big Park, Peter, that you went to see, and I think we had about 8 braces in the tree. It was planted by a past Prime Minister, so it was really important. The Prime Minister wasn't, but the tree was. We did that, and I would say 2/3 of those within 5 years had been completely destroyed by the cockatoos. So the tree's still there, the branches haven't failed, and that bracing would have been done 15, 20 years ago. So again, oftentimes these things go in to help us feel better, not necessarily to do a hell of a lot for the tree.
That's right, yeah.
But if I was writing specifications, and that's next week, and I know that, but if I was writing specifications for a support system, I would suggest that the client be issued in writing a maintenance and replacement schedule. And Cobra says 12 years. So I'd say, probably a 3-yearly inspection and adjustment, and a 12-year replacement if you're going to be serious about it. But as I said, I think they're largely about keeping us somewhat placated. So yeah, so this is saying, look, it's 1 person an hour to 3 people a day. So it'd be level 4, size of the part, probably be somewhere around that, and probability of failure, probably somewhere you could say, maybe 3 or 2. Well, there's 2 at 100,000. That was our most risk averse people. So if we look at people doing risk assessment, there's a broad, we bring to any risk assessment that we can't actually physically put a measurement or a diagnostometer onto it. We look at it based on how knowledge impacts on that, how our knowledge and our expertise. And collectively, the knowledge should give you a reasonable mid-range benchmark. So again, this was the most risk-averse group, had it down at 1 in 100,000.
So if you're saying likelihood of failure group 2, are you starting off like at the red end?
Yeah, they were starting off at the red end. Yeah. I wouldn't have started off at the red end.
I think there's a problem right there.
Yeah, yes. But again, you've got to understand that that's what I'm saying is the one end. So even if you took the most cautious end, the risk associated with the tree was such that they shouldn't have done anything.
Hmm.
And at the end of it all, they all agreed and understood that that was the case. It's just that emotional thing that you get caught up in. I would show you another tree, and I'll see whether I can do it without giving Derek any ideas where it is. It's my classic 4 tree that I use. If I can find it very quickly, I will, but if I can't, I won't. Yeah, here it is. So this tree here is my classic 4 tree. It's had a failed inclusion, a cupboard door failure. It's rotating. It's a stringy bark, a Eucalyptus eugenioides in some areas. You can see that there's certainly been some damage here, and it's doing some good adaptive growth. So anything that's got good adaptive growth going on tells me that the tree is responding appropriately.
Are you saying that your risk of likelihood of failure is group 4?
Yeah, so it's somewhere right in the middle. It's something that makes me think, okay, it's not a great tree, but it's not a horrible tree. It's about bang smack in the middle.
Mm-hmm.
It's interesting, if I were to put that then, Mona, over a childcare centre, would that change the likelihood of failure?
Change the people's worry more, concern more.
Yeah, people would be worried more, concerned more, but the likelihood of failure doesn't change. And yet for us, it does. As arborists, regularly, we look at it and we say, oh, you know, it's in a school, or it's over a caravan park, or
The consequence is higher though, if it did fail.
The consequence might not be any higher. It might be that the target or the occupation rate's higher. Or the occupation, what's in it is more valuable. We for whatever reasons, we rate children more valuable. We rate good-looking people more valuably than ugly-looking people. So my favourite man is a man from Collie who got hit by a tree, and he got 2 media entries only. Rebecca Anjoli, who was an attractive 19 or 20-year-old out of South Australia, gets about 100. And the little girl from Pitt Town, Bridget Wright, gets thousands and thousands because she's a cute little kid. You know, kids don't get killed by trees very often. In fact, far less often than grown-ups. Why?
They got more sense.
They move faster.
Yeah, both those, and the parents keep them inside more often. You know, but any time that a child gets hurt, it always garners far more media attention. Other than, you know, if you're under 35 or so and you're relatively good looking, male or female, then you're more likely to get it than once you're my age, Peter. You or I get hit by a tree and
Nobody cares less.
Yeah. Person hit by a tree is what you read. It's about the end. So
Mark?
Yes.
We're going to have time maybe today to talk about tree compartmentalisation as we discussed last time.
We will do tree compartmentalisation very easily and very quickly.
Thank you.
The reason I say very easily and very quickly is because we'll do it in the way that I said I teach a 4-year-old. If 4 and 6-year-olds can get it, most arborists can get it, hopefully. So yes, we will have plenty of time for that. It'll take us about 10 or 15 minutes to go through, that's all. This is agronomy damage. Agronomy is all the way along the east coast of Australia. And it's funny because I didn't read the headings. I just looked at it and said, boy, looks like liquid amber. May not be, might be om. But those big oval holes just let you know that it's agronomy. Agronomy spinicolis, or the decay, or banks, Carajong longicorn, or Poinciana longicorn, common name. And it's
this one was Acinigundo, and they also like the casuarinas around the area too.
Yeah, and the casuarinas don't get affected quite as badly. But one of the reasons that ASA has a problem is it's one of these trees that doesn't have a very durable timber. That is, it's got low levels of extractive. So once decay gets going in it, it goes very rapidly. And that's the same of any of those trees. It's responsible, this beetle's responsible for probably 2/3 of the willows in Australia. And until recently, we only had female willows in Australia. And so there was no sexual reproduction, no seed produced. It was all bits breaking off. And these guys are really important in helping break them off. So yeah, neat little creature. Pholinus. And Derek, these are great shots that show that, again, the response, I don't know what species it is. It looks like a uke of some description, maybe Saligna or Denii.
No, it's actually Crimea maculata.
Is it? There we are. Okay. Should have guessed it by the platelets of bark, but anyhow, you can see that asymmetry in the stem again. So you can see that more tissue is being pushed out further out. It's a fairly small tree though, by the looks of it, is it?
Would have been about 350, 400 diameter.
Yeah, so remember that trunk size does have a bearing. Maddock showed from some of his work, and subsequently Bond and Gruber has shown that as the trunk diameter gets bigger, the effects of TR becomes less significant. And once you're over 85 centimeters, it pretty well falls apart. So smaller trees are a little bit more problematic. But again, this is a Crimbia, so a Crimea maculata, fairly durable timber, fair amount of extractive. So unlike the maple, this is a lot better at resisting problems. Again, nice big Pholinus, and you can pick this as Pholinus really easily in this one because the fruiting body is quite fresh, and you get that mustardy color underside on the fruiting body. So, and again, if you wanted to have a guess, why are these there?
All that started out with mechanical damage.
Yeah, lawnmowers.
Yeah.
You know, it's just an inevitable part. And there's another great reason why mulch around trees is just such a valuable thing, is it keeps equipment further apart. I won't go into that one. We looked at it very briefly. The Genopolis, it's at the base of a tree that's dead. It's a saprophyte and not a pathogen. It's not even a weak saprophyte. The only time you'll see it is when the tissue is actually dead and it's in and going. It's got to lose moisture. Cavity in a brachychiton. Brachychiton is one of those unusual trees. It has lots and lots and lots of parenchyma in rings. Is that same lightning strike?
Yep.
It is.
So that's 12 months later. That's all of the reaction wood, all the wound wood.
This is all wound wood here. And then you'll see that the insides rot out very quickly because it's got so much parenchyma. It's like cutting a big wound in yourself and leaving a big wound opening. Lots of living cells, whereas most trees don't have anywhere near what brachychiton does. So it's a really unusual tree. The other thing that brachychiton gets is a weevil of the wood, and that really does help spread fungi. Weevil are often good at spreading hyphae and mycelium around. So,
Mark?
Yes.
We had QTRA the other day with Mike Ellis, and he said that trees with a lot of parenchyma are better at reacting to decay. But are you saying?
Okay, so yes, decay
advances faster?
No, let's talk about our decay in different groups. So we have decay that attacks dead cells. That's our saprophytic decays. And then we get decays that are weakly pathogenic, like our Pholinus, which will come around and kill some tissue, but it's not going in through all the tissue. And then we get true pathogens, and true pathogens kill living things. And so when you've got a lot of living tissue, and I can show you brachychiton if you want for next year, I'll make a note now. I'll show you some cross sections. It lays down its parenchyma. Its parenchyma will last for decades. So the living cells inside it are just phenomenal. And then they'll have these bands of fibers. And when a pathogen gets in, it kills those living cells very rapidly. And so those living cells then break down and are gone. that's not the same sort of fungi, the same sort of organisms that are attacking woody tissue. Woody tissue is made up of lignin and cellulose. There is cellulose certainly in the cell wall of parenchyma, but you've got to kill the cell and get the water out somehow or other to take advantage of it. And that's a very different process. And so we'll look at that in a fraction more detail, Michele, when we look at compartmentalisation. And if you read this great book called The CODIT Principle, it's produced by the ISA. It works off some of the German research, the English research, and we'll talk about all three when we look at compartmentalisation. All three of them go hand in hand. It's sometimes been called compartmentalisation of dysfunction, and Michele, you would have heard Mike use that phrase. And the dysfunction is we're removing water. Fungi will not grow underwater. It's as simple as that. Okay, so to get fungus to grow, we've got to get water out of it. And as wood dries out, it becomes more vulnerable. So whereas what's happening in parenchyma is it's living, we've got to kill it and then let the water out. And that does it a little quicker than it does in woody tissue. The reason for that is wood is strongly, or the cellulose and hemicellulose and lignin combination is highly hydrophilic. So I've got a desk here at my in my office. It's nigh on 200 years old, and it's still got moisture, and it's still got probably 25-30% moisture in the timber. It holds that from the atmosphere. So it's hydrophilic. This last one is two-spotted mite and a hibiscus. Spotted mites usually aren't a problem for arborists. They're not the clearest shots, but you can see the spots on them. How do these mites get around? No, they don't have wings.
From other animals, birds and things?
Yeah, rarely. My youngest son said to me one day when I was driving him to school, he said, "Dad, aren't you glad spiders don't have wings?" You start thinking about it, they don't. So most spiders run around, but these things are very small. How do they get around? The answer is they use a thing where they parachute themselves around using web. So they'll spin a very small length of web, maybe half a centimetre or so, and that's enough to increase their surface area such that they can be blown around with wind. And there are a whole pile of caterpillars that do the same, exactly the same thing, that are dispersed by this process of parachuting around with this little thread. In fact, we just mentioned one, Xyludus, the big Kossa wood moth. The female is flightless. How do they get around? The answer is they do this process of wind. And its technical name is called ballooning, and it makes sense. They just create a thread that parachutes them around. Happy with that? Okay, so what do we know about compartmentalisation? We hear it all the time. We've heard it talked about. And last block round, we saw, I'm pretty sure it was the last block, we saw how fungus moves through vascular tissue. So first of all, let's get our walls 1, 2, 3, and 4 correct. Okay, I want you to do the hand movements with me. Wall 1 is up and down. I can see Jan not behaving. Jan, wall 1 up and down. Okay, and that's the easiest way for the fungus to travel because there's long tubes. A single hole in the tube opens up a really long access. Because to block that tube up, the tree's got a tylosis or gummosis produced, and that might not happen for quite some distance. So that's our weakest. Wall 2 is into the middle. Wall 2 is into the middle. And the reason that happens that way is there's already vascular alignment in that direction. Those little blocks called rays, little building blocks, and we'll have a look at them on some images in a few more minutes. They allow for movement inwards rapidly because they've got an orientation that way. Not only have they got an orientation, but they've got cell-to-cell connectivity to move water and solutes and elements in and out along those rays. That's what they are. They're a transport system. So we've got a water transport system, then we've got the secondary transport system, the rays, and then the axial parenchyma go with the vessels going upwards and downwards. So
Is
we've got
that only in the sapwood, Mark?
Right?
Is that only in the sapwood?
No, the orientation is still the same all the way to the center of the tree.
Mm-hmm.
And so because there's big long cells that allow quick movement, it's quicker and easier to move inwards. So that's wall 2. Wall 3 is radiating aroundwards. Okay. And so the next direction that the fungus can spread is around. There's no alignment of any cells aroundwards. So that's slow. It's very slow because I've got to go through a solid wall and then the next solid wall and the next solid wall. And it's very narrow. And we'll look at some slides in a few minutes that'll help you see that. The last way we can go is into new tissue. So in a new tissue, the cambium present at the time of wounding produces things that stop that from happening. In eucalypts, they produce kinobands. Alex Shigo said if he had seen kinobands, he would have understood compartmentalisation a decade or more earlier. Okay, that's how significant it is. Interesting, whilst we're talking about it, whilst Dr. Shigo did publish the concept of compartmentalisation and he made it something of importance, he did so based on a research paper on fire damage to poplars that was done in the 1920s. So keep some hope there that all you've got to do is come up with a bright idea and present it in a unique way, and you can make a great living out of arboriculture. You don't have to be that necessarily creative. You just got to look at what's actually happening. So I think it's important to keep that in mind. And his interest, Shigo's interest, was in how decay was spread and how it moved in a tree. So wall 1 up and down, nice and easy. Wall 2 into the middle. Wall 3 radiating around. Wall 4 is coming out of the new tissue. So we talked about kinobands. They're pretty obvious walls, but wall 4 can be really subtle, and it can be subtle in terms of just a couple of cells. In fact, it can be just one cell. And the way that tree does it is it chemically alters the walls around it. Instead of having a cellulose and lignin cell wall when it matures and dies, it uses or incorporates in a lot of a chemical called suberin. It's one of the ways. There's several other chemical methods that can use it. Suberin is quite common to be used. I've got it in fig quite easily. And suberin is waterproof. And the experiment is this, and I think you've got to do it. I've been saying it for years. You've got to get a piece of pure cork. None of this refabricated. Get a good bottle of Grange Hermitage or something like that. Okay, pull the cork out, throw away the content. Okay, you don't want the bottle and the content. That's useless stuff. You just want the cork. Bury the cork in the ground. Put a little marker. Once a year, do yourself a favor, go back and have a look and see how little damage is done to that cork. Why? Because it's not digestible by most things. That's why we used pine bark for so long, because it's high in suberin. That's why pine bark is such a horrible mulch, because it doesn't break down. It's not a good organic mulch. It's almost inorganic. You can have, pine bark down for a decade and very little decay. Decorative, effective at moisture, still lets moisture in. So don't throw the pine bark out in preference to mower damage, but good wood chip is still in my preference the most ideal mulch. And Australia has done a better job of that than most other places in the world, by the way. I just noticed a comment from Amy. If everyone had trees over their roofs in this neighbourhood, or even half, this probably would not stick out like it does. Yeah, look, Amy, you're absolutely right. Tree problems are usually that people don't have trees on their property, particularly the ones with neighbours. And I remember going to one locally here, and the guy said, look, I'm sick and tired of all the falling leaves. And that was my answer, is if you had a big tree that was overhanging his property, you wouldn't care about it. The fact is you don't have a tree, and that's your responsibility that's causing the problem. And so, yeah, we tend to lose a good balanced focus on the situation. So let's have a look at some interesting cross sections and slides that'll help us understand compartmentalisation a bit better. Share my screen. First of all, we're going to go back here, and I've got to move this to the other side. So there's some indexed in here. Ah, no, not there. I've got my screen enlarged now. What have I done wrong? Let me go back and start photos again. That's better. Okay, this is the first one that's really interesting. This is a spike mark inside a palm tree. Okay, you all see that? Palms compartmentalize. Just like trees, based on their vascular alignment. Let's have a look at it. They've got a transport system that goes up and down. There's weak, gone wall one, up and down, it's lost it. They don't have rays, no rays in a monocot. So there's no wall two. The next one's wall three. That's everywhere else around the wound. That's it here. Everywhere else around the wound is this area here. And then the last way is wall four. They don't produce any new tissue. Some monocots do. So Dracena Draco, for example, produces, it's got a cambium, produces secondary thickening. But in the case of palms, there's no wall four. So it's just got wall one and wall three. But it works perfectly. This area here is more lignified and has got more suberin in it. It's got suberin for a role here. The role of suberin on the cortex, the periderma on the outside of the trunk, is it's the bark. And then we give palms crap, and I understand why. You know, they're not the prettiest and the most desirable on occasions. But that's one periderma, one outer bark area that's produced, that's going to last the palm potentially 50 or 100 years. That's pretty amazing when you think about it. Tree bark is constantly being shared and lost, and you know, this is a one time only. So lots of suberin to stop things drying out. If we get air in, then we can get fungus in. If we get fungus in, decay starts. So when the climber went up and spiked this palm tree, he damaged it. Palm trees have a lot of parenchyma. This parenchyma was able to develop a response. So, you know, it's simply protecting itself. And there's compartmentalisation in a palm tree. Who thought they'd ever see that, hey? Now, let's have a look. I'm pretty sure I've got a wall four shot. I'm hoping I do. I do, thank goodness for that. This is a fig tree. And this is one of those trees that has lots of parenchyma. And so it is a little bit more susceptible to some of those fungi like Phylinus noxious, which has changed its name, by the way. But for the sake of Phylinus noxious, causes real problems. And this fig tree split in half. Here's some compartmentalisation going on here. This is chemical, stopping the spread. But just along here, there's a really light band. And hopefully you can see that. It's darker in colour there, but the actual cellular tissue is lighter. And that's a wall 4 response. That's where the cambium was at the time the tree was injured.
Those other dark lines are the margins of the fungi, aren't they, Mark?
Yeah, but they're, unfortunately, Peter, they're fungi that came into the wood after it was cut. I cut a perfect sample for myself, and this is a sample out of the US, where we sent it to the US for use over there. And indeed, that's secondary things in there, scleroidal plates and reaction zones from fungi, from it sitting on a damp floor in a shed at Shane's Park, like a bad man. So once we got the one great specimen for ourselves, we didn't care. And then I had a couple of colleges say to me, can I have one? And then we thought, oh, we better send one to America. And by then it had already been damaged. So we do have a perfect specimen in the collection. There, by the way, is the CODIT thing in a, and if you, I'll leave it on, if you can use, does everyone know how to use snippet?
Yeah.
Yeah.
Snippet for yourself. It's a neat little drawing. That's a Kath Russo drawing. 1, 2, 3, 4. There is a textbook out there on urban tree management that has compartmentalisation incorrectly defined in terms of wall 4. They have it as the occluding tissue. It is not the occluding tissue. And you'll remember, I may not have shown you, I'm pretty sure I did, evidence of wall 4 versus bark. And it's definitely bark in occluding tissue. So the tissue that goes over the wound has a layer of bark between the wound and the new wood. Did I show you that? Okay, we'll show that then. Wall 4, of course, as I said, you get it in these massive big kino bands. They make it pretty obvious. And here is that stem as it was cut down, and you can see the light colored line. Can you see it there? That's that highly suberized zone. And that's also what causes ring shakes. The other thing that's interesting is, notice where the wood is. Let me ask you this question. After the fig had a split, was wood laid down evenly or symmetrically or not non-symmetrically?
Non-symmetrically, does one side is bulging more than the other? I guess it's
it's putting a lot more tissue on further out. So this is one of those situations where the tree, in inverted commas, knew biochemically, was aware what was happening and was seeking to adjust and adapt itself. So it's a really great example again of trees doing what trees are meant to do. So yeah, see something like that and you have an absolute ball. Okay, let's go to some microscopic slides now, if I can. And I can by doing Windows key E for Explorer on a PC. So it opens up the files by date, photos, anatomy. Am I not seeing anatomy? Anatomy.
Just above. That's it.
Not seeing anatomy there at all.
You were hovering on it a minute ago.
Was I?
Yeah.
Go line, Peter.
Where's it gone?
Go down. Stop.
Yeah.
Yeah, I don't know why it's not in sequence. So then we're going to do workshops. And anatomy. Okay, so let's have a look at some microscopic shots and see whether we can get some pictures in our head. And we'll look at all sorts of different things. I'll get this off to one side. This is a piece of gymnosperm, okay? And we've done this. This is transverse cross-section. So we've got the carrot and we've just simply cut down and made a round disc. That's all this is, a round disc that's 4 microns thick. This is late wood here, early wood here, and these are tubes. These are very long tubes. Let's see if we can see it from another perspective. Ah, okay, it's not the best. Okay, these are long tubes. If I was fungus and I got in here, I would grow up here very rapidly because there's just a long tube. Nothing's to stop me from growing in here. Only thing that stops me from growing in there in the dead wood inside the tree, so the heart wood, is water. Water stops the growth. So if
what about species that accumulate a lot of kino in the
A
In
lot of
hardwood.
extractives, yeah. So if I've got more extractives, breaking through, let me get my mouse to show, breaking through these walls becomes harder.
Okay.
Going up and down is not so hard. Okay, so wall one is so accessible. But if you look at this, this is simple. This is a gymnosperm, very simple. So this is a conifer of some description. You can see these little tubes here. They're the rays going inwards. This is what we call a uniseriate ray, or a ray that's one cell wide. And those are longer. Let's see if we can have a look at a couple of those. There they are. These are little block-like units. And these particular ones just break the rules. These are trachea rays. So they're fairly unusual, but you can see that that's moderately long again. So it can move through those fairly quickly. Okay, most of them are smaller and blockier than that. I'd have to pick up a random one that was more an unusual exception to the rule. So let's see if we can find some rays. This is an angiosperm, so it's, sorry, that's gymnosperm again. Let's see if I can get you to a nice set of rays.
Yeah, you had it.
So again, we're looking at the same process, and that just shows you that's a great little example. That's a slow growing species. 1, 2, 3, 4, 5, 6, 7, 8 cells of new growth in a year. So it's probably an alpine region gymnosperm. Oh, sorry. No screen. I should be able to see my screen. Yeah. Okay. Yeah. So it's just coming up at the wrong spot. Okay. Now, not very clear again, but the rays are, you can see, so this is rays going this way. They're blue. They're stained with cellulose. They're stained blue here, lignin stained red. And again, if you look here, this is axial parenchyma. So this is, again, one of those unusual conifers. About somewhere around about 16% of our conifers have tissue that goes up as well. Okay, it's axial parenchyma. And you can see, again, these blocky cells. Can you see that? Okay, so moving up and down the tracheids or the vessels, they're a lot bigger. We'll go have a look at some hardwood in a second. Get past things. Those of you who question whether there's spiral thickening in cell walls, this is using a polarizer, and you can see the spiral being formed. Isn't that amazing? Lovely. Okay, so there's some there. So we're in the right section. Just got to get to a good shot of it. There's a ray from the top. So this is, there's actually a number of rays here. So this is a, looks like Quercus. We've got vessels. Yes, it is Quercus, amazing. Got some vessels here. We've got these big open things. These are either axial parenchyma or fiber tracheids, that is their transport orientated material. There's a ray here, that little single ray, that's a single cell ray. Another one here, ray, they're uniseriate rays. And then here we get this massive big multiseriate ray. And that's Grevillea, that's Casuarina, that's oaks. The things that we in Australia like to call oaks, like she oaks, river oaks, are named so because they have the same thing of big, massive big rays, followed by uniseriate rays. So there's major, and so this is a very easy transport. And you can see here how long that ray cell is. It starts there on that corner, finishes there. The next one starts here, finishes there. Can you see how long they are? Would it help if I blow up more? Let me blow it up more.
They're not very long.
Oh, well, now, that's all relative, isn't it? I agree to you. That's less than a millimeter in length. But how big is it compared with the diameter of that little tube there?
Oh, wow.
Lot
Diameter is twice as much.
3-4 times as much.
Yeah.
And let's have a look at the wall thickness here. If I've got to break
It's
down the
not
wall,
much.
which wall is going to be easier to break down?
The
That
sun
wall?
Yeah.
Or the big
sun
wall at the end here?
no, the one on the rise.
Yeah, so it's about how I've got to move, how the cells are orientated and what they are. So this is a cell. Let's have a look at this cell here. Starts where the top is there, finishes down the bottom there. Now let's go across. That's 1, 2, 3, 4, 5 or 6 cells in wall 3 direction, going back this way, 1, 2, 3, 4, 5, 6. It's about the same as 6 diameters. So I can either burst through 1 ray cell wall or 6 of these. It's going to take 6 times longer to move around through this. And whilst these are old and lignified now, they're still not as thick, anywhere near as thick as each of the cell walls on these. So it's going to take a longer period of time. Does that give some context as to why wall 3 is just a hard yakka for fungus? It's got to break through the wall. Let's have a look how they're connected. So there's connections in plant cells and in, just going to try and hide that, Peter. I don't know how to do that. No, that's okay. I can do it with a thumb roll.
So basically, the species that resist better to decay because of their wood structure.
The way that
the
yes.
way that the rays are, how thick the walls are, it's just a genetic thing, and perhaps environmental as well, depending on the growing conditions.
Largely genetics. So things that have, for example, not big rays or even big rays, but produce lots of extractives, are going to be more decay resistant. Things that don't have a lot of rays, or that when they dry, they get little micro cracks in them that allow air to get in and then the fungus to get in, they are going to decay more. So if you get something like Chinese elm, it drinks a lot, but it's fairly decay resistant. Compare that with English elm, and I think we'd agree that English elm just doesn't seem to have a great degree of compartmentalisation.
Yeah.
Let's look about eucalypts. If we talk about our boxes, they generally are fairly decay resistant trees. Our red gums, they're called red gums because they've got lots of extractives. They're fairly decay resistant. And you get something like your mountain ash, and it's a very poor compartmentalized, very low levels of extractive, and it grows so rapidly that when it dries, it gets these little micro fissures. So you can put a regnans log into the ground and put a grey box or an oak log or a casuarina log all equal size beside it, and you'll push the regnans over in 5 to 10 years just by hand. It'll have been completely rotten away. It's not a very durable timber. Is it useful timber? Yes, it just can't be exposed to weather. Okay. And realistically, that's where our fungi, when we're out in the wild, that's where our fungi are exposed to. So I'm just going to try and find you some rays going sideways in a good shot that'll let you get an idea of those. And for all these things, there's lots of exceptions and rules and things that don't fit in well. Maybe I should do it from, oh, no, okay. Yeah, I can't turn it. But again, you can see this. There is a ray cell. It starts there. It finishes there. And if I go up here, that's 1, 2, 3, 4, 5 cells again. So I would expect the inward movement to be at least 5 times faster than the outward movement. Does that make sense?
Yeah.
So inward movement along the rays will be 5 times more than wall 3 going around, because there's 5 times more cell walls to break down. Let me give you another example, Michele, because I can see the confusion on the face. We're going to go from Footscray into Melbourne, and at every traffic light, we're going to build a brick wall. Okay. Now, it's going to take a while to get there, but that's on my one. On your one, because you're young and fit, and for every brick wall that you put in, we're going to put 4 additional brick walls along that pathway. Will that slow you down more than me? You bet.
Mm-hmm.
Okay, so that's what's happening here. Now, I can't get you exactly, but that's the start of a vessel. It's not the full vessel. But now let's just try it from there to there. Let's start counting how many cells there are and try and get an idea. 1, 2, 3, 4, 5, 6, 7, 8. 8, and then we're going to have probably 1, 2, 3,
About 8.
by 6.
About got me. It's roughly the size of my thumb, so that's 1, 2, 3, 4, 5, 6. About 7.
7. Okay, so on this particular thing, and that's not full length of the vessel yet, we might say 10. There's 10 lots of those, 80. So we've got, it's going to move up and down heaps faster than it will move inwards. At least 8 times faster inwards than it's. Do you see why now it looks like the walls are there? Because as I'm going along, I hit one of these rays, and I apologize that it's not orientated the way that it we see it. I hit one of these rays, and I'm automatically going to start going in the ray rather than trying to get to the next cell beside. And the next, this is just more convenient. I'm going to follow the highway or the transport system. And
path of least resistance.
yeah, who said that? Mick. Hi,
Yeah.
Mick. Absolutely, you got it down perfect. It's a path of least resistance, remembering that water is involved in this process. That is, as dysfunction is created, one little hole in this vessel, and I can go from here to here. There's a vessel starting there, and it's still going down here. It's hard getting a full length of a vessel. I want to go out, and it's not going to. How do I do that? I close that out, and I go back to the index. That's the way to do it. So yes, it's a purely a numbers game, and you can start to work this number. Now, here's an interesting shot. Might not look very obvious, but there are tubes here. Let me open it up on a big screen. See the little tubes? When these were alive, these were connection points. These are called plasmodesmata. Well, it's a nice big word to make me sound very photosynthesis. But these are little tubes that connect cells together that transport's going on. And fungus can get through that. Remember we saw a few weeks ago? So again, how big they are and any little break in those are going to have an influence on it.
So is that a sieve plate at the end of a vessel element cell?
No, that's just interconnecting cells in what we call the symplastic tissue. So the rays are symplast or parenchyma. So parenchyma has to talk to the next cell in the parenchyma connection and the next cell. And the way that they talk is chemically, and they transport through these things here. So if you go out and put a systemic chemical on a tree, it's using plasmodesmata or connecting cells. When it matures and woodens up and dies, then they no longer function. When that's just cellulose, that functions quite effectively. And there's a lot of stuff. I mean, we don't have time to go through a whole cell physiology thing tonight, but next year it's something that I'm more than happy to look at, is spending 2 or 3 nights looking at how cells actually work. But if you can remember, there's these tubes that are connected together that connect living cells. And again, they become a problem for transport. They also become an advantage for the transport system. And this will be my last one, I think. And hopefully it's given you some concept behind what compartmentalisation is. And this is a way of stopping movement up and down. I'm sure we've done it before, but it doesn't help us to do it again. Move this back down again. And this is this thing called tylosis. Oh, I love tylosis. Okay, tylosis occurs when the adjacent parenchyma to a vessel's dead. It's woody tissue. It's just a big dead woody tube. Okay, it's made up of vessels made up of lots of cells stacked on each other called vessel elements. And they get told when they're born, Mick, it's a horrible thing, harden up and die. And so that's exactly what they do. They harden up and die. And that's usually a matter of a few weeks for that to happen. So they're very short-lived cells. The problem is you don't want things to get inside your cells or it causes problems. So here's a root off Eucalyptus grandis and it's been cut, and that's fine. But look what starts to happen. We're getting these bubbles developed. Can you see these little bubbles inside? Let me zoom in, not perfectly in focus now, but those little bubbles are the adjacent parenchyma cell wall gets to stretch, and it goes through the little plasmodesmata, it herniates through, and it starts to block off these vessels. And that's how it stops it going up and down. Of course, that kills the adjacent parenchyma, but that's okay. It stops the spread of decay. If you look here, that one's been completely blocked. That one's been completely blocked. That's what it's working at doing, is blocking that off.
And this process is called tylosis, is it?
Tylosis, yeah.
How long would that typically take? Is that minutes or hours?
The problem is, Peter, we get to do it experimentally in a non-natural environment. So I don't know. I'm imagining probably more in the hours than the minutes.
So, for example, if you're cutting and painting using glyphosate, it seems to work much better if you apply it immediately after you've cut it. After just a few minutes, it doesn't work as well.
You probably get away with it with a few minutes. By the time you get to an hour or two, I think you've probably lost it. And again, what we don't know is the answer to that question, because I'm cutting this is a cross section here that's probably about half a mil thick. And all that we're doing is looking at it forming with all the pressures involved after it's been cut. So it won't respond in the same way. So Peter, it may be down to minutes. I don't know of any experiment that has been done that would allow you to inspect it at the end of the cut route, but I'm sure with some clever microscopy you could. That sounds like a fun project.
Yeah.
So maybe someone has, because if it's fun, it's a good way to get research funded to do it. But yes, this particular one was within 2 hours or so of the cut being made. The tylosis was quite obvious. So yeah, it doesn't take long.
The uptake of glyphosate in a cut stump will have a little bit more to do with just tylosis, though, won't it? So we're breaking that hydrogen or the water, the siphon.
Yeah, that's right. It's got to get. So what it's going to do is going to start filling up these tubes, and then glyphosate will be transported in part through the apoplastic system until it hits the symplastic system. So there's 2 transport systems. Well, it's multiple. There's 3 major ones. So the apoplast is through dead tissue, cell walls, and the vessels and tracheids. Then there's the sugar conducting system through the phloem, and then there's this living cell conductive system that systemically moves things, and that's what we want to get our glyphosate into, because it affects parenchyma. It's a herbicide that affects living cell function. That's how it kills. No point killing dead cells. Okay, you go out tomorrow, get yourself a nice gun, put it at the head of a corpse and shoot them. The police won't come around and arrest you for killing somebody. They'll arrest you for interfering with a corpse, which is a different deal, but at least you won't get charged with murder. And same with glyphosate. Glyphosate has to kill the living. So it has to get into that symplastic system. And so, yes, there's a whole pile of chemical reactions going on, including productions of those chemicals like suberins to try and stop moisture loss occurring. And so the longer you leave the cut, the less effective glyphosate's going to become.
So just to carry on from that, your glyphosate is getting drawn into the root system by the phloem, which is traveling down, and also the living tissue.
Yeah, that's right. The living tissue is connected around. So around the vessels, there are lots of living cells, the rays. So here, for example, this has been stained up with iodine and potassium iodine. It's its grandis. The rays in this are very small and only 1 cell wide. So eucalyptus rays are hard to see. That's why when you cut through them, you don't see rays. They're very insignificant. And that's the living system. It's transporting. And you'll see it's around the vessels. It's around the vessels because as water and chemicals come up, solutes come up through the vessel, these living cells have got to get what the tree needs. And so they have these little proteins that grab things, and they have these tubes that allow things to come through. And so they'll take in things. They're taking the things that the tree wants. Again, a little bit closer, and you can see they don't look very significant, and they're not.
So the living tissue is the axial parenchyma?
And radial parenchyma. So parenchyma is the thing we call these living cells parenchyma. That is, they live more than the 6 or 8 weeks of harden up and die. For something like cotinus, that's maybe 18 months. Some of the oaks, 18 months, 2 years. Something like brachychiton or ficus, maybe 10 or 15, perhaps 20 years. Something like brachychiton, maybe 5 or 6 decades. It just depends on the species. So parenchyma is long-lived in comparison, a lot longer lived. And parenchyma can form rays inwards and also can form around. Let me show you. I'm pretty sure I can do it quickly. Maybe I can't. Let me just see. No, not the greatest, but it'll. So this parenchyma. Yeah, let me just zoom in. This is brachychiton. One of the most amazing plants, if you ask me. You'll see there's a little bit of blue around this vessel. Can you see that? Let me zoom in. See, this is parenchyma around that vessel. Cell after cell after cell, there's a little round tubing on it. Same thing around this one. Okay. Then there's the ray here. That's parenchyma. Okay. Then there's this ray here, and this ray goes, this is the bark here. This is the phloem. It's the active phloem is here. So it's only got one layer of active phloem. That is one growth increment of cells that are moving sugars. The rest of it's pretty well known. 2, 3, maybe 3 years there, but this here is a vessel going, sorry, a ray going right through the bark. So transport goes right through the bark to the outside. What's it getting from the outside?
Oxygen.
Oxygen, very important. What color's the bark of brachychiton?
Green.
So it's photosynthesizing.
Photosynthesizing, yeah. So it's producing sugars right at the bark. That's actively photosynthesizing, and it's also getting rid of waste products out there, carbon dioxide. Sorry, oxygen, horrible waste product that causes harm, and taking in carbon dioxide, so gases exchange. So lots of things are happening through this transport system. By the time we get to here, the phloem's just completely dysfunctional, or close enough to dysfunctional. If we look here, these fibers, you can see here, these fibers here are hollow. These fibers here are almost completely full, and these fibers here aren't doing anything. So they're no longer conducting. That's a solid piece of wood. If I was a decay organism and I hit that, it's nowhere that I'm going. And this is the same on the inside. If we could go back another side to the left, you'd find that this is really solid in here now. And so this is a really good natural barrier to the spread of decay. But it's got this axial, this radial parenchyma that almost is so solid that you get a band of it. And so if something can break through all of this and hit this zone here, it's highly vulnerable. And it's in bands like this over here. So it's lots of parenchyma, lots of fibers, lots of parenchyma, lots of fibers. A little bit like we saw earlier on in that fig sample, where you could see the banding. And there are a number of trees that do it. Erythrina is another one. Erythrina, really good compartmentalizer until it comes to pathogenic fungi. And then it degrades and rots so rapidly. Make sense?
So that big blue ray, that's leading into a lenticel, is it?
It's just going out of the bark there. They're just enormous. And there are lots of other things that do this in plant material. Another one that has these really great diverging rays through the bark, and you can see the ray goes all the way through, doesn't stop, is Tilia cordata. I love Tilia cordata for exactly the same reason. So, yeah, and Mick, I hope I can say this without you being upset, but this is why we need to constantly be looking at these things because I know you were at a workshop with me where we went through a lot of this stuff, and your brain's like mine. Unless I'm using it all the time, I forget it. You know, I haven't traveled to Thailand, I think, in 4 or 5 years. And I know that when I get over there, my tie is going to be so rusty that no one's going to understand a word I'm saying. So it's exactly the same with this stuff. You've got to be using it, otherwise you lose it. And I know we looked at some of these in a presentation. That's one of those, part of one of those. Well, let's go here. It's even further out. This is a trachea. We haven't got to the end of it. From there to there. Let's go close up to it. From there to there, one whole length. That's nothing. We've got, I can see a single ray cell there.
Hold on. Which image are you looking at?
Sorry? Can you see a brown image on the screen?
Yeah, we can see.
Yeah.
Yeah. So this is
Which image you looking at?
Can you hear me? See me? Hello?
Well, yeah, I can.
Yeah, Michele? I think Michele's lost us.
Yeah.
So I think his computer's gone on the fritz. So yes, that's a trachea, and it's longer than that photograph is wide. So that photograph needs to be turned 90 degrees, if you can imagine that. And you can see here, if we zoom in, these are fungal cells here growing along. And you can see the size comparison-wise, by being able to go up and down very rapidly, means wall one's the weakest. You can see these ray cells here, less slower movement. Okay, there's a ray cell there, one whole ray cell. That's only 2.5 times on this particular species. So this one will move a little quicker in than it will outwards. Michele, can you see it now?
Yes, I can. I had issue with internet.
And then these little connections here, these are pit connections. Okay, so there's a little cellulose plug. That's why you're seeing the blue there. Whereas these are fenestrator window connections to the ray cells, the parenchyma. And what happens is the membrane of the ray cells right beside there, so that the cellulose cell wall of the membrane has this big surface area in contact with the water. Okay, that's going up and down the trachea, because it's got to get its chemicals, the little proteins and the little holes, to grab what it needs to take in and then put into the transport system. If it's a species that's got axial and radial parenchyma, those systems will intermesh. And so things will go up and around and down and all over the place. Moving things upwards is fairly easy. Moving things downwards fairly hard. So many of our chemicals we can get up to the top. A lot of them are harder to get down to the roots in terms of beneficial chemicals. Okay, and that's because it's got to go down through the phloem. There's no downward movement through the xylem. Xylem is always vertical. Phloem is up and down. And phloem is chemically controlled. So we create a pressure differential in terms of chemicals. It moves sugars up and down. It moves stuff in the phloem up and down. Xylem is controlled by pressure, and the pressure is a negative pressure, atmospheric pressure, pulling out the water. And that's in part why, in most cases, as an overall generalization, rainforest species, particularly understory species, grow a lot slower because they can't photosynthesize as fast. They can't get enough water because the humidity in the air and the atmosphere around them and the lack of wind throw has issues. When they become emergent, something like the Brazil nut or something like ficus in a rainforest, once it comes out of the top of it, then the atmosphere changes. And so they can grow faster. But the canopy trees, not the emergent trees, but the canopy trees grow slower because they're humid, and then they've not got this ability to get water up. To get water up, you need a pressure to draw it, a negative pressure to suck it up. And humidity means I can't get as much out because there's already moisture in it. If I take all the moisture out of the air, I can suck it up at a phenomenal rate. So it's a difficult balancing things. And that's one of the reasons why Australia has some of the tallest angiosperms in the world, is we have what we call cool and temperate rainforests. Tropical rainforest is too humid. Good. Any other
Mhm.
questions on, does that give you a little bit better picture on what compartmentalisation is about? It's about water. It's about how cells are aligned, their size and comparative things. It's about chemicals that are in the tissue, this stuff here, and all three of those work together. And trees that are highly decay resistant have really great chemicals in these walls.
And are the species that flood part of the hardwood with water or not? Or it just has an high water content because it's not evaporating, kind of?
I've got to think of that question again. So are species that flood?
Yeah, they hardwood, or they keep their hardwood at much higher water content.
What do you mean by flood?
I mean, they keep a high moisture content in the hardwood.
If you were to take something like the docks of London, where we've got Syncarpia logs from Australia in the water, then nothing's going to happen to them. Marine organisms will eat them away, but decay won't, because they're saturated. You take and there's been great people doing it, both in New Zealand and Australia, things like kauri in New Zealand, digging up buried specimens that have been kept moist by the soil, where they're not allowed to dry out, and they might have moisture content of 80 or 90%. Flooded cedar, red cedar is Tuna ciliata. Tuna ciliata has been pulled out of old creeks and rivers and logged, and it doesn't decay because it's underwater.
So these are all anaerobic environments, aren't they?
Yeah.
So same as a cavity in a tree that's constantly filled with water.
Well, even if it's constantly filled with water, so if you took a log and you submerged it underwater, or it's dense and it sunk, and you ran water over it constantly, very little oxygen is going to be in that, and certainly not sufficient to support fungal growth. So that's one way you can stop it from having issues. The other thing, you can dry it out slowly in those conditions. So I know there was a lot of work done, for example, on trying to dry out brushbox, Lophostomus convertus timber, because it wants to check. So if you dry it more slowly with water, that has an advantage as well. But if you're talking about species that grow in riparian zones, whether they are more decay resistant, I don't know. It's going to depend on a whole pile of variables.
Mm-hmm.
The species that are affected by riparian conditions often have either slightly different biochemical processes for breaking down starches or sugars to make it available. So flooding has an issue. We've got a problem at the moment in Sydney that we're referring to as cytoroxylin decline, and it's really quite extensive. Probably, I don't know, 5% or so of cytoroxins are in stress or decline, and increasing just based on the wet weather. Some species don't care if it's wet at all. Things like ficus has a process of transporting oxygen, and then we get plants that can transport it perfectly, like our mangroves.
Taxodiums.
Taxodiums, yeah. And lots of rainforest species do exactly the same. Why do rainforest species need to do it?
Because they're periodically flooded.
Yeah. Rather than use the flooding, let's just talk about saturation. When the soil is saturated, yeah, they might have saturated soil for 20% of the year. So they've got to have a system, and there's some really chemical good stuff on it. Apoptosis occurs, cells start to blow up. You get arenchymal roots. You get the lenticels start to increase inside. You get active transport of gases. So there are lots of techniques that plants are using to deal with these things. So that's more a question of the biochemistry for that plant than anything else. And we're still at fairly early stages of understanding all this. The research, Shogo was blessed in that he got money to do the research. When I was young, lad, my father was responsible for a research facility in poultry here in Australia. I grew up in that until my late 20s. I can tell you the Department of Agriculture in New South Wales now has gone from having a staff of 30 odd dealing with that research to 0. Forestry Commission at Pennant Hills had 2 mycologists, had a pathology department. I know they're knocking it all down. It's all gone. So, you know, we really don't have a lot of research going on. So a lot of these questions are just up for the curiosity of individuals to start working out. And then the occasional person that says, yeah, I'm up for doing something stupid. Peter, as I said, has been playing with one recently that now he's shaking his head and saying, yep, I'm seeing how stupid it can be.
It's not easy.
It's not easy, and it takes time and effort and money. And by the time Peter has it as a paper published in the Journal of Arboriculture, I'm guessing he'll have spent probably $20,000 to $50,000 on it. He'll eventually want to do it because he's just like a dog with a bone.
Yeah. Maybe not quite that much, but because I had some great help from people who were able to, were willing to let me use their land and trees and so forth.
But yes, I mean, you know, if you wanted to go through and do as I said, a really good statistical analysis looking at biomass, then
yeah,
doable, but
that would blow it out significantly.
Yes, that's what I was inferring. So if that's done, then hopefully got a little bit on compartmentalisation. Again, feel free to throw Peter questions. I just finish off with one little case study that might just help the thinking process for you during the break. About 2 weeks ago, I got asked to go look at some Conophenix alexandrae and some Washingtonia robustas. The people had 3 Conophenixes die within 1 week, one after another after another. Their head just tilted over and they died. And then they had some golden cane palms nearby do the same thing. And then they had a Washingtonia nearby look really sickly. And they did the right thing. They went to the Botanic Gardens. They took a sample in. The Botanic Gardens said, there's phytopithium in your sample. It's usually not a problem for, you know, advanced plant material. But that's all we could find. And I looked at it and I had the advantage of having seen all that material, and I said, okay, I'm pretty comfortable with knowing what it is. Does anyone want to guess what it is and why?
Some sort of insect like a weevil.
Well, let me ask you a question, Peter. That's a good thought.
About herbicide.
Let's think first of all in our disease categories. How likely is it that a biological disease is going to affect 3 trees equally within the same short period of time?
Not likely.
It starts to get and then how likely is it a biological disease then is also going to affect not even closely related plant species?
Almost none.
Almost none, yeah. So and so when I saw phytopithium, I thought, oh, okay, we're so far off the mark, it's ridiculous. So who said herbicide damage?
I did.
Yeah, so it could have been herbicide damage. What you're saying is it's abiotic. It's an abiotic disease.
Oh, saturation of the soil for too long a period of time.
Yeah, that could be, but a lot of palms develop parenchymal roots. So, and it was a fairly well drained block. So the very first question I said to her is, how long beforehand did the lightning strike occur? She said, oh, how did you know we'd been hit by lightning? I said, well, if I had to guess, that would give me the perfect sudden death of the trees that took the direct hit, less damage to those that were involved in the arc out, the golden canes below, and the Washingtonia above. And indeed, the property had a direct lightning strike, did property damage, did about $15,000 or $16,000 worth of damage to the property. And they never linked the two together. Okay, but they just, again, this process of saying what explains what I'm going, and working from, not from the end, but let's start to narrow it down in that diagnostic process. It's unlikely that it's biological because all 3 palms died in short succession. Other palms were affected, so it gets even less likely. So it could have been herbicide damage. And that would have been my next question is, what did you do when you did the plumbing repair? Because that's a common place where, you know, we end up with accidental application of herbicides and people thinking they're doing the right thing. Plumbers sometimes thinking, oh, I'll just stop the damage occurring again.
Yeah, you do stop it.
Yeah, that does happen. And, you know, plumbers like arborists aren't always the brightest people, unfortunately. So yeah, so that's the last for this year, guys. Next year, we'll be back at it again. If you'd like to send in your images, that's fine. If in the meantime there's something you want to discuss, email Peter, he'll email me. Vicky will assure you that I might take a week or two to find the time to give you an answer back, but I will get back to you. I'm not here to do your consulting jobs, but I'm happy to discuss the overall things and help you improve in your journey on that process. So guys, have a great Christmas. If you're free and you want to come over to Houston and spend a whole pot of money playing tree anatomy with me, you're welcome. Unfortunately, Kentucky's already sold out, so it has to be Houston or you don't get there. But we'll be back next year with Arbos again. I believe that's correct, isn't it, Peter?
Yeah.
And yet